We're going to start today off with a little review. So pause the video to try these out. Feel free to copy the examples down as well. But here, this is a lot like what was off of GIF 4.1 from a while back. You want to find the value of the derivative graphically, if it exists, at each indicated extremum. All right, so if you need more time, just pause the video again. So notice here we have 2 points that are indicated. So we would say that f prime of x is equal to 0 when x is 0 and when x is 2. Now the value, so f prime of 0 is going to equal f prime at 2, which is 0, slope of the tangent lines. For b, f prime of x, we kind of put this into 1 because there's only one extrema here. So we would say f prime of x is actually undefined when x is equal to 2. We could have done that for a. We could have just said f prime of 0 is equal to 0, f prime of 2 is equal to 0 as well. All right, our second example, we want to use analytic methods to find A, the relative extrema where they occur, B, the interval or intervals on which the function is increasing, and then C, the intervals on which the function is decreasing. This would be a no calculator question. So pause the video to give this a try. All right, so if you're ready to go over this, you can let the video play. If not, pause it again. But first we want to find f prime of x. So I'm going to use the quotient rule here. So f prime of x is going to equal our low times d high minus our high times d low all over low low. So this turns out to be negative 2x squared minus 18, and then we'll get a plus 4x squared all over the denominator. So this will give us 2x squared minus 18 over that denominator. All right, so now we'll ask ourselves 2 questions. Where is this derivative 0? So we'll say f prime of x is going to equal 0 when the numerator equals 0. So when 2x squared minus 18 equals 0, should be an 18. I was already dividing. So now x squared is going to equal 9. So x is going to equal plus or minus 3. All right, where is our derivative undefined? When our denominator is equal to 0, but x squared is always positive and we're adding a 9, so that's never going to be 0. So now we're going to make our first derivative number line. We'll have our negative and positive 3. Now, if it helps, we could factor this. We could say it's 2 times the quantity x minus 3 times the quantity x plus 3, again, just over x squared plus 9 squared. So that denominator is always positive. So if I tested, let's say, a negative 4, I'm going to get 2 times, this will definitely be a negative and another negative, so that's going to give me a positive. If I tested 0, I'd get a positive times a positive, so negative divided by a positive is still negative. And then if I tested 4, everything is positive. So this means our function is increasing, then decreasing, and then increasing again. So we can indicate we've got a relative max here and a relative min here. All right, so let's figure out these values here. So we would say f of negative 3, again, our function, let's squeeze this in up here, f of x is equal to negative 2x over x squared plus 9. So this becomes, we'll have a positive 6 in the numerator, and then we'll get an 18. So 1/3. and then f of 3 becomes just negative 6/18 or negative 1/3. All right, so for part A, we would say the relative max is y equals 1/3 when x equals negative 3. And the relative min is y equals negative 1/3 when x equals positive 3. E, our intervals where our function is increasing, is from negative infinity to negative 3 and from 3 to infinity. And decreasing in between the 3's. All right, next let's take a look at the AP calculus problem I assigned yesterday. Here we're told the first derivative of the function f is defined here for all x's between 0 and 2 inclusive. On what intervals is f increasing? So they already gave us our first derivative here. So it says the graphing calculator is okay. Now if you use CAST, that's fine, but if not, we could still just use the solve feature. And we could determine where f prime of x is equal to 0 or where it's undefined. But that's going to be a lot of work and it's going to use up a lot of time. So instead of actually working off of the first derivative with these two questions, let's go ahead and graph. Let's just do the graph of the derivative. So let's just go ahead and type that into a graphs page. And this is what we should be getting. So here's our interval from 0 to 2. Now I just made my x-axis just go from 0 to 2.5. So again, this is f prime of x. So we want to decide f is increasing when our first derivative is what? Positive, right? So our first derivative is positive between here and here. Afterwards, that cuts it off. Right here is the 2 anyway. Now you could just trace on the calculator here, but it definitely looks like we're between what, 1 and about 1.691. Because if you also see it calculated the 0 right here, so that's giving us this value right here. So that gives us B. And we can find it relatively quickly doing this method. All right, next let's take a look at example 2 that we started yesterday. So hopefully you guys had a chance to go through the InspireDoc 4.4. The answer here was that the max area is 12 radical 3 square units when the dimensions are 2 radical 3 units by 6 units. So yesterday in class we came up with the function for the area function here. We wanted to take the derivative, and then we wanted to set that derivative equal to 0 and see what x values caused it to equal 0, and undefined as well, this would be never. But here we're getting plus or minus radical 3, but because x is between 0 to 3, we just use the positive radical 3 only. Now you could make a table of values, that's perfectly fine, but I also want to show you, we know we're on a continuous function on a closed interval, so we could still say it's the extreme value theorem. If not, I could show you a little bit quicker, we could do the second derivative test as a way to justify. If you don't do this, you have to definitely state this is the extreme value theorem. So we find our second derivative, and when x is radical 3, we get a value that's negative. Therefore, it's concave down around that critical number, and we have a relative max, or really an absolute max, at x equals radical 3. So then that makes our base 2 radical 3 units. Our height is 6 units. So then we get the max area. 6 times 2 radical 3 is 12 radical 3 square units when the dimensions are 2 radical 3 units by 6 units. All right, so now we're going to take a look at example 3 off of yesterday's handout that I gave you guys. We're going to design a 2-liter can that uses the least material. We want to know what the dimensions of this can need to be. So a can is in the shape of a cylinder. The 2-liter means we're dealing with volume. Now the formula for volume is the area of the base times the height. So let's go ahead and draw a little cylinder here. So this would be our radius, and then this would be our height. Now we want to minimize the amount of material. So using material here, this is actually surface area. And we want to minimize this. If we minimize the material used, we minimize the cost eventually. Another nice fact we need to know is that in 1 liter, there are 1,000 cubic centimeters. All right, so looking at the volume then, we're going to say the volume is going to be the area of our base here, which is going to be pi r squared times our height. Now we already know the volume that this can hold, so that's going to be 2 liters. So we're going to say 2,000, keep everything in centimeters here. And then that's going to equal pi r squared times our height. Then I want to write this out for surface area. I'm just going to use S. So our surface area is going to be, we have 2 circles, so we have 2 pi r squared. And then if we were to cut this down the center here and roll it out kind of like the end of a paper towel roll, you cut it and you lay it flat, you get a rectangle. But the length of the rectangle is going to be the circumference rather, so that's going to be plus 2 pi r and then times our height. So if we were to lay out this rectangle, this would be the circumference, the length, and then we still have our height. But I want this all in terms of r. So I'm going to go back over to my volume formula. This is a little helping equation here, and I want to solve it for h. I want to replace the h with something in terms of r. So h is just going to equal 2,000 divided by pi r squared. So now this becomes 2 pi r squared plus 2 pi r times the 2,000 over pi r squared. And I can simplify this now. So my surface area function is going to become 2 pi r squared. I'm going to get an r still in the denominator, so I'm going to get 4,000 over r. And then this is what I want to find, or take the derivative of. So we want to find s prime of r, taking the derivative of this first part. Now pi is just a number, so this becomes 2 times 2 pi, so we're going to get a 4 pi r. And then this right here is really 4,000 times r to the negative first. So we're going to get a negative 4,000 r to the negative second, or we can put it over r squared. Next, we want to figure out where this derivative is equal to 0. So s prime of r equals 0. S prime of r is undefined. We can answer this first part. That's when r is 0, but it doesn't make sense to have a negative or a radius of 0 because r needs to be positive here. So we're going to set this first derivative equal to 0. What I'm actually going to do is multiply everything throughout by r squared. So we're going to get a 4 pi r cubed minus 4,000. We'll set it equal to 4,000 now. Divide by 4 pi. So r cubed is going to equal 1,000 over pi. And r is just going to equal the cube root of each one. So we'll really get a 10 over the cube root of pi. It's not a nice looking answer, but we're going to leave it that way. All right, so I want you guys to continue with this. I want you to justify. Now we're definitely not on a closed interval here. So I want you, let's go through and use the second derivative test for extrema. So you guys go ahead and finish this. We'll go over this tomorrow. Just to show you here, if you want to pause the video, you can check your answers to the evens, what I assign. I'm definitely going to go over number 32A tomorrow, but I want you guys just to try these again, see what you come up with, get questions ready for me. All right, so continue to work on yesterday's assignment. And now on pages 214 to 217, try 4 more problems. And then the AP, page 29, 76, and 77. The calculator is okay, but don't use any of the CAS features, meaning you can't use the solve feature, you can't use the derivative feature. And just a reminder, test is coming up on Monday. So take care. Please let me know if you have any questions.